Hello, I am Kartanak Paul, and today I will be talking about optimal robotic assembly sequence planning, a sequential decision-making approach. As seen with the James Webb Space Telescope, we have reached the maximum capabilities of the current Space Launch System vehicle's capabilities, and so in the future must send up multiple launches and assemble these structures in space. It is pertinent that we are capable of performing this autonomously. As such, I have been looking at current efforts to form this assembly sequencing and notice key areas of improvement. In this paper, we propose a sequential decision-making approach to this assembly problem. To explain our methods, we utilize this running example, which we codify into this graph structure. We utilize an assembly by disassembly approach, where at each point we would consider what connections we need to remove to get to the disassembled state. If we note that we can combine duplicate nodes in this graph, we can generate this consolidated state space. We additionally note that if we take a complete graph search method, then it would recover an optimal assembly sequence. And so we developed this idea of graph exploration assembly planners, or GEAPs, which utilize the directedness of our graph to produce optimal results with even single visitation. We showed that value iteration, Dijkstra's, Bellman-Ford, and our own ORASP search method that we propose are capable of generating these optimal disassembly plans. We deploy our graph search algorithms onto these 5 example scenarios and compare them to the state-of-the-art, and showcase that we can not only produce these optimal strategies, but also do it up to 5,000 times faster than the state-of-the-art. We additionally note that our graph is equivalent to a deterministic Markov Decision Process, and so can also utilize reinforcement learning to achieve this goal. We specifically use a DQN, or Deep Q network, which maps the current status of the assembly to the best action. We deploy our strategy, our DQN, on scenarios of increasing size, and showcase that we can not only outperform a distribution of 100 random sequences, but also recover the optimal strategy in many of these scenarios. We began with the problem of finding a fast and efficient multi-agent robotic sequence planner, and showcased, using our sequential decision-making approach, that we can deploy both optimal graph searches and near-optimal RL algorithms to solve this task. Thank you for your time.